All right. Well, let's get started. Okay, so I'm watching my own GitHub repository, and I'm waiting for the day for the number of forks to reach the number enrolled in our class, and we are getting closer. But it also means some students have not done this yet. So again, I'm going to be using GitHub to kind of post all of the course lectures and notes and all of that. Rather than using Canvas. Canvas is fine, but it's, this is like designed for this kind of stuff. So, so once again, in order to pull it onto your computer, so this is the where I'm simulating pretending to be a student. You just change into your GitHub repository, okay, wherever it's stored, and it might be a long path, and you might have to type a whole bunch of things to get there, okay? And then, and you can kind of see, and so right now I have, I'm only up through 1.2, I don't have 1-3 or anything like that, so I'm going to go ahead and do git pull upstream main, and again, once you have your remote repository set up, that does it, okay? Git pull upstream main, that's really the only command you need to do. And then if you want, you can also do git push, and that will then push it to your own repository online, right? So here I can click. How do I view the forks? I don't know how to do this. I don't know how to, I thought. Okay, well, anyway, that's where it is. Okay, so and now 1-3 is on here. So again, the command is git pull upstream main, assuming you have your remote repository set up. Yeah, question.
So when I go to my fork, there's a sync fork button. Does that do the same thing?
So okay, so you can do that. You can sync it on your thing, and then you can just pull it. All right. So on your computer, so yeah, you can do sync your fork, and then it will sync your fork on GitHub, and then from there, if you want to get it onto your local machine, you can just pull, and you can just do git pull, which defaults to yours, and you don't have to specify upstream. But you can also, but that requires you to have your browser open. Yeah. And this you don't have, you don't have to enter anything. You just git pull upstream main. So, okay, but yeah, that's an option. All right, over here, I'm going to go ahead and exit this side. This is me, the professor. This is my account, and I have 1-3 here, and I'm going to launch Jupyter Lab. And that spins the wheels on the system here, and here we go. Let me hide my right sidebar. Let me close this terminal. We'll close this one. Discard changes. Let me shut down this kernel. Okay, and then all right. So we'll open 1-3 basic data types, and you know what? Let me go ahead. I'm going to clear all outputs here. All right, and let me. Okay, so today, I have this numbered wrong. Sorry. Well, I don't like to, I hesitate to push changes after the fact. so I'm sorry, it's just going to be numbered 2-1 on the notes there. Okay, but here we'll just start looking at some basic Python stuff. Some of this has already been covered in your data camp homework, but I'll present it a little bit kind of formally here. A lot of this is coming straight from our textbook, Think Python, which I hope all of you have downloaded, and if you haven't, start reading the first few chapters there. Okay. All right. So yeah, let's talk about variable types. Okay, so there's a few different types of data in base Python. You've got a bunch of important data types. Other important data types do exist, but you can only kind of work with them after loading something like NumPy or Pandas. So one thing to note is that in base Python, there's no such thing as an array. There's no such thing as a data frame. Those are data types that you can only work with after loading NumPy and Pandas, which are at this point almost essential. Okay, especially if you're approaching Python from a data science perspective. If you're going to use Python as a general programming language, they might not be necessary, but if you're going to do anything related to data, you absolutely need to load in NumPy and Pandas. Okay, but regarding our data types in Python, these are kind of your most commonly used values. Okay, you got strings, integers, floating point numbers, booleans, and the none type, or the null. And so, in R, we call these characters. This was integers. This was type double. This was logical, and none was called null. But it's kind of the same kind of ideas, right? So you have character information or text information in strings, integers, floats for things with decimal values. And then we have also very important data structures, such we have sequences, which include the list, the tuple, and the range object. And then we have mappings like a dictionary, and there's other things like bunches and stuff. And then you have sets, and you kind of have these binary type data here. Okay. Anyway, you can always ask, what is the type of data that you're working with? And so if you put 2 in quotes, that's going to come back and say that's string type. Okay. What about just the number 2? It's an integer. 2.0, however, is a float. And then true is a Boolean. And none is none type. Okay. Note, true is spelled capital T, R-U-E. All right. And that's different from, say, R, where it was all caps true. All right. These are the operations, the math operations that exist in base Python, and there's only a few. This is perhaps for some people, this is surprisingly limited in terms of the different math operations you can do. So versus in R, a lot of kind of math functions are built in. You can call in math functions in Python, but you have to load in the math library, which is part of your base Python installation, but you do have to load that module up. All right, so you got addition, multiplication, subtraction, division, integer division, and modulo arithmetic. All right, so you have percent to get the integer remainder, and then you can raise exponentiation, and you can do absolute values. So here, anytime I've got x and y are both integers. And in Python, you always know something's an integer because you have no decimal dot. And so if it prints out without a decimal dot, it's going to be an integer, right? And if you take 2 integers and you add them together and you store them somewhere, you're going to get an integer, right? If you take 2 integers and you multiply them together, so x and y are both integers, you multiply those 2 together, you also get an integer. So the number 50 is an integer, and it shows up as 50, no dot. Okay. You do division. Division always results in a float, even if there's no remainder. All right. So if you do 10 divided by 5, it's the number 2. Okay. But it's always going to be a float, and Python will always let you know that the number you're dealing with is a floating point number, even if you think it's an integer, because it will always include a decimal there. So to distinguish the integer 2 from the floating point value 2, you've got, it's going to say 2.0. Okay. I covered this in 102A about kind of limits of floating point arithmetic, but I don't know if you guys are familiar with that just yet. Yeah, question?
What if you use floor division?
Floor division will result always in an integer. Okay, so floor division will always produce an integer. Okay, here we can test that out. I'm not going to save this, but I can do 10//5, and that results in an integer. And even if you do something like 10//3, floor division always results in an integer here, right? And then you'll have a remainder. So 10 mod 3 is going to be 1. Whoops. And that's also an integer. So floor division and modulo arithmetic always gives you integer values. Yeah. Okay. You do anything with if you mix a float and an integer, it always results in a float, right? So here I have 10.0, and if I do 10.0 plus 5, I'm going to get 15.0. 10.0 times 5 will give me 50.0 to indicate that these are floating point numbers. Okay, so floats are used to represent things with decimal values. All right, and one kind of a thing about floats is you can't treat them like real numbers, right? So we often think of like decimal values as like real numbers because you can do like square root of 2, and you can represent pi and stuff with float, but they're not real numbers because there is a limit, right? So floating point numbers on most systems have about 16 places of decimal precision, and that's not infinity, right? Real numbers, you have infinity values, and we can't represent infinity values. The largest value you can represent on float is 1.797 times 10 to the 308, which is a pretty big number, but it's much less than infinity. Okay, so it's basically just a tiny bit less than 2 to the 1024 power. So with float, I can do 2 to the 1023 power, and I can represent this number. Okay, I can do 2 to the 1023 plus 2 to the 1022 plus 2 to the 1021, and I can get a number that gets closer and closer to this limit. Okay, but if I try to do 2 to the 1024, I get an overflow error. Right? I'm just simply not able to represent this as a calculus on the thing, right? And we've encountered overflow errors probably in our childhood when we were working with like a simple calculator, right? So if you recall your first calculator, you probably, I imagine you tried to do like the biggest number, right? You did 9999999 times 9999999, and then you get an error. And you're like, oh man, the calculator can't even figure this out. Okay, but that's basically what's happening. It's just saying like, on your calculator, there's only 8 digits, so I can't represent anything bigger than 9999999, right? And so if you try to do like 9999999, even plus 1, at that point, you get an error because it says, I just can't do it. I can't do it because I don't have enough space. And that's basically what we're doing here, right? So on the computer, we say, well, we're going to use 64 bits to store this information, and there's a limit. There's a limit to how big of a number you can represent. And so when you hit this, you're reaching an overflow, okay? There is a much less kind of common error on this calculator. What would be the opposite of an overflow? Way to go, well, underflow, okay? But what's an underflow error, okay? The underflow error is what if you did 0.0000001, okay? And then you said, take that number and divide by 10. What will you get? Okay. The calculator outputs 0, but is it actually 0? No, right? The calculator to this thing, 0.000 is like 10 to the negative, what's the smallest you can represent? 10 to the negative 7 or here. And then if you try to like divide that by 10 or divide by 100, it's going to be like 10 to the negative 8 or 10 to the negative 9, and your calculator can't do it because there's only 8 digits on there. Okay, there's something similar. I didn't put an example on that, but there is an underflow error where basically it's not able to represent anything smaller because anything smaller it's going to just think is 0. Okay, floating point numbers do not work the same way real numbers do. All right, so what is this? 1 plus 2 divided by 10. What is that? It's not a trick question. It's 3/10, right? 0.3, okay? And I'm going to say A is equal to 1 plus 2 divided by 10, and we get 0.3. What is B? I got 1/10 plus 2/10. This should equal also 0.3, okay? But on the computer, and I say, okay, is A equal to B, all right? So in regular old math, you'd say A is equal to B, okay? But on the computer, if I do a test for equality, which you use the equal sign for, A equal B, it comes back false. It comes back false. And you're like, what? How? Right? This is probably, if you're not accustomed to floating point math, this is surprising because in regular real math, these two values are equal. But in floating point math, these two things are not equal, okay? And if we ask, well, what's going on? Underlying these things, I say print it out to 20 decimal places of precision. A actually gets stored as 0.299999999 whatever, okay? And over here it gets stored as 0.3000000 something. And so the computer doesn't recognize these two things as being equal. They actually have slightly different representations as far as the ones and zeros that get stored inside your computer. Because it has a way to represent 1 and a way to represent 2 and a way to divide the 10, and when you do that computation, it results in this in the bits. But then if you do the computation this way, it results in this thing, which is just ever so slightly different bit sequence. And it says, okay, well, these two things aren't equal. And you might be like, what? How's that? But that's just kind of a side effect, okay? And again, you might have encountered something like this on your calculator, right? So what if I did 10 divided by 3, okay? On my calculator, I get 3.33333, right? And then what if I do this number and I multiply by 3? What am I going to get? Yeah, I'm not going to get 10. I'm going to get 9.9999999, okay? And basically I'm asking, is 9.99999 equal to 10? According to the calculator, it's not, okay? And then, and that's basically saying, is 10 divided by 3 times 3 equal to 10? In regular math, yes. 10 divided by 3 times 3 is 10. Calculator math, which is basically a slightly modified version of computer math, okay, floating point math, they're not equal. 10 divided by 3 is 3.3333. 3.33333 times 3 is 9.99999, which is not the same thing as 10. And basically something similar is happening on the level of ones and zeros inside our calculator or our computer, okay? So you have something called is close, and this is kind of a way to kind of circumvent this, and you can say, well, is A close to B? Okay, and then we'll say, yeah, 9.9999 is close to 10, and that'll say true. But how do you know if somebody actually wants 9.999, which is a separate value from 10, versus what they're trying to think is 10? And you know, there's ambiguity there. Integer type in Python uses variable amounts of memory. And so if you need to use lots of memory to store a big integer, it can. So we can do 2 to the 1023, and it's going to show you all the places of precision for 2 raised to the 1023rd power. Over here, we just got an approximation, 8.98 something up to this many decimals times 10 to the 307. And here it actually calculated all of the values. I can do 2 to the 1024, and it actually computes all of the all of the values here. Whereas with a floating point number, 2 to the 1024 resulted in an overflow. And I can keep going. 2 to the 1025, it's able to compute all of these numbers, no problem. Okay. You have the power operator, 9 squared is 81, no problem. There's no square root operator in base Python. You have to import the math module if you want square roots. No worries. But you can do 9 raised to the 0.5 power, and that works, okay? So if you want to do something like square roots. Okay, pi, there's no such thing as pi. There's no such thing as exp, there's no sign function in base Python. Okay, all of these things result in errors because they're not in there. But you can import the math module. You do import math, and now you can reference the square root function. So you have to say, we're going to do some math. Inside math, what's the square root? Inside math, what's the value of pi? Inside math, what's the e function? Okay, inside math, what's the sign of pi over 2, right? So you can do math.sign of math.pi over 2 and something like that. Okay, and you get all of these values. So that's what we have for Python. Okay, I've forgotten. First view quiz answer is the letter A. A as an apple. A as an apple. Yeah, question.
I don't think the view quiz is open.
Oh, it's not open? Did I mess that up? View quiz for week 1 Friday? Where is it? Oh, you know what? I forgot to add it to the modules. Thank you. Week 1 Friday, lecture view quiz. Okay, it should be there. And the first answer should be the letter A, I hope. All right, so we have true. True is the Boolean. If you put it in quotes, that's a string. All right, and there's only one accepted spelling of true and false, and it's capital T, lowercase rue, capital F, lowercase alse. So if you try to do all caps true, it's going to think this is like a variable name, or if you just do the letter T or something like that, or the lowercase t, it's going to all result in this thing is not defined, this name is not defined. Okay, Booleans. All right, strings, you put things in quotes, single quotes or double quotes, and these get stored as strings. And there's a couple string functions. One is like length, and you can say how many characters are in there, including spaces and punctuation. And you can take a string, and you can do stuff like multiplication. You can even do addition. So, how are you? Fine, 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 fine. 4 times message 2 or something like that, right? Okay, variable assignment. I think this is all familiar. We just use the equal sign. So unlike R, R is like the only language I know that does this little weird arrow thing. But we join the regular languages that use an equal sign of assignment. We get n equals 5. You can print that out, no problem. Okay. All right, this is a little bit more CS, and we don't have to worry too much about it. Okay. But variables in Python are technically pointers, okay? And so, versus someplace like Java or C, you define like basically a bucket that is able to hold values, and you say this bucket is going to hold integers, and anytime you try to stick something that's not an integer, you get an error. Over here, I just do x equals 4, okay? And what this does is it creates a pointer called x, and this pointer x points to a bucket that contains the value 4, okay? And anytime, and so 4 is this kind of this immutable thing. There's just one 4 defined, okay? And it's its own thing, and we just have x pointing to it. Okay, and so we don't need to, in Python, we don't like declare variables, all right? We don't have to do stuff like int x equals 4 or something like that. We just say, hey, x. And Python is what we call dynamically typed because it's just going to change where this name, x, where it points, okay? So right now it's pointing to the value 4. And when I do this, it's gonna do 3 things just in rapid order right after the other. It's gonna change where x is pointing. It's gonna point to a 1. And then it's gonna point to a string that contains the characters hello, Hello. And then it's gonna point to a list that contains the values 1, 2, and 3, okay? and that's it. Okay, and we can kind of change all of this, no problem. We don't have to redeclare our variable x and stuff like that. And this is R has some similar features, and so if you've only had R and Python so far, then it might not be too surprising. Versus if you're coming from C or Java, it might be like, oh, that's nice, or you might be worried like, oh, aren't you going to run into problems later in terms of like things that are strongly typed, languages that are strongly typed. Okay, you can pretty much choose anything to be a variable name as long as it follows these rules. Okay, names can have letters, numbers, and underscore characters, so no special characters other than letters and numbers. Okay, names cannot start with a number. All right, no symbols other than the underscore, no spaces, and it can't be a Python keyword, and these are your Python keywords. Okay, things like for and if. You don't want to create a variable named if. Okay, and obviously not true or false and stuff like that. So these are your keywords, but as long as it's not one of these, can be a variable name. Okay, naming a variable is there's a joke that it's like one of the hardest things, and that's because you want to be able to read a variable and understand what it contains, without having to like refer back to like when you originally defined it. So you want it to be clear and concise. It's kind of, we say, use English words, which is okay. We're in the US, so that's probably fine. But sometimes you're coding in a different country in a different language, but it's still kind of recommended that English happens to just kind of be the default language for a lot of things. Okay, and you don't want to use special characters. So basically, just use things that show up on your US or English keyboard, and not kind of accented values there. Okay, so these are values that aren't great. Okay, we have S equals 101533, SID equals 101533. These aren't. It's hard to know what this represents. Okay, this is also way too long. Finnish Meteorological Institute Observation Station Identification Number 101533. Okay, so that tells us like, oh, okay. Thankfully we have tab completion, but again, this just makes it harder to read your code, right? So better things, FMI, station ID. You can do either snake case or camel case. So snake case separates words with underscores. Camel case separates words by using capital letters. And that's what we have. Okay. There are some conventions that we recommend when naming variables. Okay, so if you're going to have a list that's going to contain multiple things, the name for that list should be plural. Okay, so here I have a list that contains fruits. Okay, and so we don't want to call it fruit. It's better to call it fruits versus fruit. Okay, and then even better to kind of indicate what kind of values we might encounter in this list. If we say this list is called fruit names, that's going to indicate to us that the values inside are going to be strings. Okay, or if you had fruit counts, okay, then it's going to indicate that we're expecting like integers, count values, right? Or fruit weights or something. Kind of maybe we're going to encounter decimal values or something like that. Something that hints at what kind of values might be stored inside the list. Okay, and if it's just a single value, then you can fruit weight and without plural indicates hints to you that it might be just a single number. Okay, and if you follow that, your code will be easier to read. And it's good for you because the person that you collaborate with the most is future you and past you, and you're not able to give past you a phone call for help. Okay, so always kind of do things that will end up helping you out later on. Document and add comments so you can kind of tell yourself in the future what you were thinking at this particular moment in time, right? Sometimes as you're writing code, you have a temptation to be funny and like put in a joke as far as like your naming stuff. And then later on, you'll be like, what was I thinking? Keep it professional just for your own sake. All right. Okay, so as far as if you've got variables that are going to store Boolean values, you want to turn these into like basically yes or no questions. Okay, so rather than writing selected, right, or fruit, okay, you want to say, okay, is selected true? Can write true? Has fruit true? Right? And these are kind of like is something selected, yes or no? Is this something writable? Can write or is writable? Okay, contains fruit or something, has fruit. This is these are yes or no questions, and that's going to help you as far as, again, understanding what it is that you're doing. Okay, I don't enforce this. Okay, when we read your code for stuff for your homework submissions, we don't enforce this. This is just like, these are good tips for how to make your own life easier in the future. Okay, as far as storing numeric values, adding anything to indicate what it's supposed to contain is helpful, right? So rather than rows equals 3, okay, you go, all right, well, you can say, all right, minimum rows, max rows, total rows, current row, something like that. Those are all probably going to be a little bit more more helpful and stuff. If we have, when we name our functions, we often think of functions as the verbs. And in English, we have like kind of present tense action verbs, and then we also have passive forms of the verb, right? And so if a function is going to actually modify an object, then you should give it an action name, versus some functions don't modify an object, but return either a modified version or looks at the object and returns maybe a value or a status or something from that thing, okay? And so those things would be kind of like a passive form, right? And these kind of principles have been applied already to a lot of the base functions within R, okay? So for example, let's say you have a list and it's going to, you're going to sort the list, okay? Then, and if it actually modifies the list, then the function should be called sort, right? If you have a function that's going to take a look at the list, not actually modify anything, but return a sorted version of it, then that function should be called sorted, okay? So we got the sorted, which will return a sorted version of the list, and sort, which will actually sort the list. So, so within Python, some of these things, a lot of these principles have been applied. So here I've got this this list, okay? I have car brand names, and I have a list Ford, BMW, Volvo, and Toyota. And car brand names dot sort takes the list and it modifies it itself, okay? So this is an action verb. So we're taking the list and it's going to sort in alphabetical order, and we can see it has the result is here that it has indeed been sorted, or it has been modified, okay? Whereas over here, this list, I've got Chevy, Audi, and Honda, and I say, okay, give me back a sorted version, okay? So this is sorted, and it gives you back a sorted version, but the original list remains unmodified, okay? If you try doing something like car brand names dot sorted, right? And you go, okay, this actually this attribute doesn't exist, and there's actually no function called sort. Okay, this this function doesn't exist. So there's some things you got to kind of keep track of. Is you can do the action that modifies a list is dot sort, okay, and then the function that returns a sorted version is sorted, and this one is not a dot sorted, okay. And so there's some stuff, and these are just things you gotta kind of have to memorize along the way. Yeah.
You still make that work though, using something like main.sort brand name?
What's that?
Can you make it work like main.sort or brand name?
Main.sort? Maybe.
With underscores.
Yeah. I'm not sure. I don't think, yeah. Okay, no, it doesn't like it.
This was main with the main of process or something.
Yeah, main's your, what is it, top level, yeah, not environments, or whatever we call it. And, okay, so we got through this notebook a little bit faster than I originally anticipated. But don't actually want to modify it. So I'll just reset some of these things. Let me go ahead and give you your second view quiz answer, which is the letter E. E as in elephant. E as in elephant. Okay. All right. Well, okay. Sorry. Well, I guess I'll give you your last one too. What is it? E and the third view is B. B as in bear. Okay. E as in elephant, and B as in bear are your second and third view quiz answers for today. Okay. Well, we will spend more time working with each of these different types, but I'm trying to think. Are there any other things I want to talk about today? So we just finished a little bit early. All right, I'll just let you guys go early, 10 minutes early today, and then I'll kind of time my lecture from Monday to be a little bit better. So sorry for the short lecture today. We'll just end it a little bit early. Have a great weekend, and we'll see you on Monday.